Welcome back, everyone. My name is Pedram, and this is where we do machine learning codes and concepts. Let's get started. All right, Principal Component Analysis, or PCA. This is our first unsupervised machine learning model that we're going to cover today. So what is it, why is it important, and what are the applications? So typically, PCA is used for reducing the dimensionality of the data in a way that it keeps as much information as possible while it's reducing the dimension. And it's going to do that by finding some axes, we're going to call them principal components, that along those axes, the data is varying most. So what does that mean? Let's pause for a second. Imagine we have a data set with only two features, just for the sake of argument, and we're going to extend it to many more features down the road. We have two features, and then these are the observations, right? So basically, the data set is unlabeled. We have x1, x2, and when I say unlabeled, I mean it is unsupervised, right? x1 and x2, right? And if you look at this cloud of data, there's one direction that data is varying most. Which one is that? Let me actually label them. So I'm going to call them A, direction B. So in which direction the data is varying most, or you can say the spread of the data is most. Yeah, A, right? So we're going to call this one principal component 1 and this one principal component 2. So this means that if I want to basically find the directions that the data, along those directions the data is varying most, number 1 is PC1, number 2 is PC2, right? And then if I, for whatever reason, let's say, if I want to reduce the dimensionality of this very simple data set from 2 to 1, then I'm going to say, I will go with PC1 if I have to reduce the dimensionality to 1, right? So the PC1 is going to become something like this. So this is my PC1, and the data is, I'm trying my best. So the data is something like this. So now we go from 2 dimension to 1 dimension by finding the most important components in the data, right? And which in this case is PC1, right? And why does it matter? Imagine you have a data set with 100 features, right? So you have x1 through x100. And these can be anything, right? So imagine you're looking at credit card default, or just for example, it can be unlabeled data as well, right? These are some simple features, gender, age, education, income, credit card balance, you name it. It can be anything, right? And then you want to visualize it. Obviously, we cannot visualize things in 100 dimensions, right? So we have to reduce the dimensionality into 2 or 3 if we want to visualize it, right? And when I want to go from 100 dimensions to 2 dimension, I want to make sure that I find those directions that save as much information as possible when it comes to variation in a data set, right? So that's the whole point of principal component analysis. And these directions, these new dimensions, are a combination of all the other features, right? So for example, I have PC1, I have PC2. In this example, I'm going from 100 dimensions to 2, right? And then each of these PCs, I'm going to write a small letter f. These are function of all the features, x1 through x100. So this is important. This is a function of all the features, x1 through x100. So it can be a linear function, we call it linear PCA. It can be a nonlinear function, we call it kernel PCA. So we're going to talk about those differences as well. But at the end of the day, this is going to transform data from 100 dimensions to 2 dimension, and now we can observe stuff here. So we can say cloud of data here, cloud of data here, cloud of data here for clustering, or many different applications that you can think of. So this is what is PCA at a high level, and now we're going to break it down, talk about the theory behind it, and all the cool stuff. Okay, so module 11, dimensionality reduction. We're going to use PCA, principal component analysis, to achieve that. Okay, so this is where we are. Unsupervised machine learning models and PCA used for reducing the dimensionality of the data, right? So now that we are familiar with all the machine learning models, it's time to become familiar with some new terminologies as well. So for example, what is feature selection versus feature extraction? What is feature importance? So let's take a look at those things. Imagine we have a labeled data set, right? So imagine your data set is something as simple as this. The target variable is if somebody has defaulted or not. So this is your Y. And your features are, I don't know, maybe 20 of these X's. It can be your income level, it can be your education level, it can be gender, it can be age, you name it, right? All these things. And here we have 20 features, and this data set is labeled. So we have seen some techniques before to reduce the dimension of the data, and my goal here is to make sure that you understand the difference between these techniques, right? So if you remember, I think here when we talked about penalized regression, I introduced lasso, right? And we said with lasso, if the shrinkage parameter is large enough, we can exclude some of the features, right? So it was used for feature selection. So that's why we call that thing feature selection. Feature selection. So we could say that, hey, we have 20 features, but if the shrinkage parameter in that model is large enough, we go from 20 parameters to 20 features to maybe 3. The 3 could be income, education, age, right? So that 3. So this is feature selection. So it means that by applying lasso, you were able to basically find the features that probably played the most important role, right, for that penalized regression. So in that case, it was, let's say, just for the sake of argument, X1, which was your income, I don't know, X5, maybe it was your credit card balance, and X, I don't know, I'm just making up these things, right, X15, right? Maybe it was something else. And that one maybe was your age, right? So this is what we call feature selection. So let me highlight it. This is feature selection. We're selecting features between 20, we're selecting them. And the data set is labeled, right? That's fine. So, and then we said, okay, this is going to give us only 3 features. What if you want to rank those features? What if you want to rank the importance of those features? And then that's where we talked about tree-based models. For example, we said random forest can do that job for us, right? So the random forest has something called feature importance, which can tell you what is the ranking of the features, right? Importance. So this is another term, feature importance. Let me actually highlight this one as well. So feature importance versus feature selection, right? And we could use feature importance to say, hey, for example, income or credit card balance was more important than age, it was more important than income, it was more important than gender, and et cetera, right? Now, lastly, here, what we're talking about in the PCA, we are reducing the dimension in a different way, right? So here, first of all, the data set here is unsupervised, unlabeled, but we can use the same example. We can say, I don't care about this default variable. I just focus on these 20 features. Can I reduce the dimension in a way that, we can explain the most variation in the data? And the answer is yes, right? So we're going to find those components, let's say PC1, PC2, and I'm going to do the same thing, PC1, PC2. And here's the difference. This principal component 1 is a function of all the features, not only, for example, X1. It's all the features that we have. This is a function of all the features. X20, and component 3 is a function of all the features. So as you can see, this is not selecting features. It's basically extracting 3 components out of those features, right? So this is called feature extraction. So let me highlight this one as well. So there's a big difference here between feature selection and feature extraction. In feature selection on the left, you ended up dropping, well, let's see. You ended up dropping 17 of those features and then pick 3 of them. So that's, you selected 3 of them. Here, you're not dropping any useful information. You're keeping all that information, but you're extracting all those 20 features into 3 components. So this is why principal component is able to keep more information while reducing the dimensionality of the data, right? So that's the difference. And obviously here in this example, I applied principal component analysis to a label data, but you get the idea. Typically, we apply to an unlabeled data to extract some important features and then later on use it in another supervised machine learning model. Okay. All right, so here are the topics, and we are going to do this in 3 parts. In part 1, I will remind you what is unsupervised learning model, and then basically what was the agenda there. And then we're going to talk about some terminologies, eigenvalues, eigenvectors, because that's the core of principal component analysis. In part 2, we talk about this, what is the optimization problem in principal component analysis, how it's doing the job, and we talk about scree plot. And finally, in part 3, we will say, why should we go beyond principal component, the linear PCA, right? What are the advantages and disadvantages? And that's where we are going to talk about Kernel PCA and the concept of kernel. And finally, we're going to wrap up this section by talking about the applications of PCA. Okay, part 1, terminology. All right, so let me quickly remind you what is unsupervised learning. If you remember, at the very beginning of this course, we talked about different types of machine learning: supervised, unsupervised, and reinforcement learning. And the unsupervised is the one that the dataset is not labeled. So you're not giving any labels to the machine. And in that sense, the goal is a little unclear. So what are we doing here? The entire point of doing unsupervised is to find something interesting in the data, find some underlying pattern, find some groups of samples that behave similarly in the data. So that's the agenda, right? And there are 2 main types for unsupervised learning ones. One is dimensionality reduction algorithm, namely PCA. This is what we're going to cover today. And the other one, clustering techniques, right? So let's look at this simple example. On the left, this is a supervised data, right? Why is it supervised? Because I have x1 here, I have x2 here, and I have colors. So these colors are labeled, right? So it can be x1, x2, and your target variable can be blue or red, right? However, on the right, we have x1 and x2, and as you can see, there's no color here, so there's no label here. But we can use some techniques. For example, we can talk about clustering this data to find the observations that are behaving similarly, right? So that's the clustering technique. Later on, we're going to talk about k-means clustering and hierarchical clustering in the next episodes. Okay, let me show you one more motivating example to help us understand why PCA is important. So just remember, guys, we don't use PCA. Typically, we don't use it in a vacuum, right? We typically combine it with some clustering techniques, or if the data is labeled, we are going to use it later on for making a meta model and do a supervised learning task, right? But here in this example, imagine you're a marketing manager and you want to run a marketing campaign, and basically you want to decide how you should segment the market, right? So let's say we have a data set, and that data set has some features, right? The features are, you are able to collect this information from your loyal customers. You know their income level, their willingness to pay based on their previous purchases. This can be survey data, right? You can ask for their age, or willingness to pay can be some levels, right? Low, medium, high, and things like that. Obviously, their gender, you know their education, for example. So imagine you have this valuable survey data and plus, I don't know, their income level, credit card history, and things like that, right? And then let's say you have 20 of these features, 20 features. Obviously, you can go ahead and use some clustering techniques that we're going to talk about them later on, but put them in different clusters, right? So you want to say, I don't know, in 20-dimensional space, I use clustering technique to find the customers that behave similarly, right? And you want to find, for example, a group that you should give them coupon. You want to find a group that you should, I don't know, make a VIP group for them, or things like that, right? So, however, you cannot visualize it yet, right? Because this is in 20 dimension. You can go ahead and apply PCA, reduce this 20 dimension into 2. It can be PC1, PC2, these are the dimensions, right? And you already know that this PC1 is a function of all those features, is a function of all those income, willingness to pay, and etc., 20 features. Okay, so it's extracting very useful information, and by useful I mean it has most variation along that axis, right? So you have PC1, PC2. Now you can basically visualize it, right? Let's say you have 1,000 customers, and then you go from this dimension 1,000 by 20 to 1,000 by 2, right? So this is, you're going to transform the data into this dimension. Now you can apply, you can visualize those clusters, right? So you can say, hey, this is my cluster number 1, cluster number 2, cluster number 3 and 4, and then now you can decide how you want to basically treat them, right? So probably making a VIP group for some, giving some these coupon discounts, and etc., etc. So this is at the high level the motivating example that why we should do unsupervised learning techniques in general. All right, now let's get into the fun part, the theory of principal component analysis. So what is happening under the hood? For that, we need to learn some mathematical concepts, eigenvalues, eigenvectors, because that's the core of PCA. So let me actually start at the very top right. Look at this picture. We are transforming it by, let's say I apply some transformation, right? I go from this one on the left to this one on the right, right? And I'm showing two arrows here for you, so the blue one and the red one. I want you to pay attention what happens to this blue one and red one after we apply that transformation, right? So when we apply this transformation, the blue one is going to remain the same. The red one is kind of rotated, right? So then this blue one, it has a cool property because after applying that transformation, it didn't change direction, right? So we are going to give it a name. It's going to be called eigenvector. So eigenvector is a vector that does not change direction when we apply a transformation. So the blue one is our eigenvector. And for this eigenvector, there's a magnitude attached to that, right? I want you to pay attention. What happens to the magnitude of this blue one? It's whatever it is, it seems that it doesn't change. So this magnitude, we're going to call it eigenvalue. So the magnitude of eigenvector is our eigenvalue. So in this case, the answer is 1, right? So in this mapping, the blue arrow is eigenvector. Why? Because it doesn't change direction. And its magnitude, its eigenvalue, is equal to 1. Why? Because you can see there is no change in the magnitude. So if the blue arrow was double, or it was even rotated completely in a negative direction, it was still eigenvector, because again the direction is along this axis, but the magnitude can be -1, it can be 1, it can be +2, and etc., right? So this is eigenvalue, eigenvector. But in order to again understand deep down what's going on, we have to talk about the mathematics detail. All right, now let's do the details of this transformation matrix. What do we mean by transformation, right? Go ahead and click on this link. It's going to send you to a simple Khan Academy lecture, and then the videos are directly coming from this awesome YouTube channel called 3 Blue 1 Brown, and check it out if you haven't already. This is a very, very awesome YouTube channel. Okay, so I'm going to show you what do we mean by transformation. Just pay attention to this green and red arrow. After applying a transformation, it's going to become something like this, right? So let me play it one more time. So what's going on here? So let's summarize some numbers, right? So we want to figure out what is that matrix that if I apply that matrix to this green arrow, it's gonna rotate, something like that, right? So as you can see, the original place of the green arrow is what? It's 1 and 0, 1 and 0, right? So when we apply this transformation, it's gonna take this 1 and 0 and send it where? It's gonna send it to 0 and 1. So this is doing something like this. So take the green arrow and then send it to 0, 1. It's doing the same stuff to basically our red arrow. It's going to take it from 0 and 1. This is 0 and 1. And then send it to what? To send it to -1 and 0, right? So 0, 1, send it to -1, 0. So if I go ahead and use these two transformed vectors, so 0, 1, and then -1 and 1. So this is my transformation matrix. So it's a simple squared 2 by 2 matrix here in this example, because we are in 2 dimension. Now this means that if I apply this, if I multiply this matrix to any vector, in this case it can be a green one and a red one, it's going to send them to new space, right? It's going to send not new space, in new, well, in this example, in new directions, right? So for example, so this is what we're going to call our transformation matrix, right? So if I And it's pretty straightforward to figure it out. Well, actually, there are ways to define it more. Now, we're going to talk about those things later on. But here, just focus on this very simple visualization. So let's look at this one more time. So our transformation is going to be, there you go, 0, 1, and minus 1, 1. So that's the answer. Now let's try a bunch of more examples together, and I bet you're going to get it. So let's see. So imagine, let's talk about the same vectors, the green one and the red one. And let's see what happens to them after the transformation. And let's try to figure out what is the transformation matrix. I want you to go ahead and pause the video and then think about it. So let's see it. Okay, so what happens? It's kind of, we go from 1 and 0 to 1 and 0.5 for the green one. What happens to the red one? For the red one, we go from 0 and 1 to 0.5 and 1. So do you find something like that there? There you go. This should be the answer. Does it make sense? Okay, let's do a bunch of more and then you will get there. Let's look at this one. This should be pretty straightforward, right? So we go from green and red to this green and red. So what is your transformation matrix? There you go. All right, let's do another one. Oh, it's shrinking, right? So this should be pretty straightforward. There you go. Okay, so find that one that's shrinking stuff. Okay, there you go. Now let's do another one. Oh, what's going on here? So you can quickly look at the new numbers or just think about it intuitively. Just one more time. Your 1 and 0 is going to become 0 and, oh, well, sorry, 0 and 1, right? So that's your 0 and 1 here. And then the other one, the red one, your 0, 1 becomes 1, 0. So this must be the answer. Okay. All right. So hopefully you get this. This is doing a lot, right? So let's do this one. We go from 1, 0 to minus 2, minus 1, right? So do we have something like this? There you go. And let's do just one last one. Okay, so we go from 1, 0 to minus 1, 0. So this should be it. I'm just following the green ones, but you can do the same for red ones as well. So that's the transformation matrix, right? So the transformation is your simple squared matrix that it's taking some vectors and then change their direction, send them somewhere else, right? And so this is a transformation matrix. Now let's talk about eigenvalues and eigenvectors, right? So imagine we have a matrix, which is a squared matrix. How can I find 2 vectors or 3 vectors, depending on the dimension of the data? How can I find vectors in that data that when I apply the transformation, it doesn't change direction? In this case, how can I find the blue vector? Okay. And then when I find a blue vector, I can, there's a corresponding eigenvalue to that vector, the corresponding magnitude to that vector as well. Okay, so let me go ahead and open this. Here's another visualization website. I'm going ahead. I think if you click on the PDF version, you should get access to this link as well. So here it is. So imagine we are dealing with this transformation matrix, right? So 0, 1, 2, minus 1. And let me show you something. And imagine this is the vector that we are interested in. We want to send it to some new directions, right? And we want to see what happens to this black vector after we apply this transformation matrix. I'm going to go ahead and show you, well, let me not show you the eigenvalues first. I want you to figure it out. So if I change this, if I rotate this black one, you see there are 2 times that the vector doesn't change direction. When I say change direction, remember guys, the red one is when we apply this transformation to the black one, right? So if this red and black are overlapped, so it means that we applied the transformation to the black one and the direction is the same. So this is once. This is another time. Do you agree? Because again, yes, the direction is the same, but the magnitude is minus something, right? So let me show you the eigenvalues. Now it makes more sense. So the eigenvalues are minus 2 and 1. So this is your eigenvector, and this is your eigenvalue minus 2. And this is your eigenvalue 1. Does that make sense? Well, hopefully I can get it there. Yeah, there you go. So we can try different matrices, for example. We can play around with these numbers and see, or you can use those transformation that we looked into in Khan Academy and see if that makes sense or not, right? So I don't know, for example, I can do 0, 1. Here we can do -1 and 0. And you want to see what are the eigenvalues, eigenvectors. So there's no eigenvalue, eigenvector. What does it mean? It means that for this specific transformation, there is no point in time that when you apply that transformation, this vector is not going to change direction. It's going to change direction all the time, okay? So there's no eigenvalue, eigenvectors. And then we can look into, I don't know, a bunch of other examples. So let's do, it can be any number, right? 2.5. And then, yeah, for this one, there are 2 eigenvalues. So this means that at twice we have, yeah, there you go. This is your eigenvalue, eigenvector, 1.71. This is your probably, let's see, find the smaller one somewhere. There you go. This is the smaller one. Eigenvalue, eigenvector, right? 0.29 is the eigenvalue. And how many of these eigenvalues, eigenvectors do we have? That depends on the rank of your matrix, right? So remember, transformation matrix is a squared matrix. So it can be 4 by 4, 5 by 5, 10 by 10, right? At most, you can have, so if it is a 10 by 10, at most you can have 10 eigenvalues. If it is 20, at most you can have 20 eigenvalues, right? And of course, it can be 0 as well. So all right, let's go back to the slides. And the last thing I want you to talk about in this slide is that, okay, we know visually what's going on, but mathematically, how can we derive these eigenvalues and eigenvectors? So it's super simple, actually. We have this transformation matrix, we call it A, right? This is our transformation matrix. And the idea is that if we apply this to a vector, if that vector remains the same, it doesn't change direction, but just the magnitude is changing, then this is our eigenvalues and eigenvectors. Again, so it's something like this. It says that eigenvector is a vector that if you apply this transformation to that, it's going to remain the same, but the magnitude is different. So that's it, right? So now we have an equation. We need to make sure that that's satisfied. So just let's go ahead and use some matrix algebra. Let's solve for lambdas and v, right? So AV minus lambda v is equal to 0. This is a vector. And then I need to factor the vector v. So it's going to be a minus lambda. Because this is a scalar, we have to put an identity matrix here. Multiply v is equal to 0. So I have an equation which is on the left side is equal to 0. So this means that either v is equal to 0 or a minus lambda I, this thing, is equal to 0. So in order to make that happen, we have to go ahead and calculate the determinant. Determinant of the matrix lambda I is equal to 0. And if you set it to equal to 0, it's going to give us an equation, depending on the rank of your matrix. For example, if it is 2, it's going to give you two equations, two unknowns, right? So you're going to solve for lambda 1 and lambda 2, and by lambda 1 you can find the corresponding v1, by lambda 2 you can find the corresponding v2. Okay, so if you're not following this matrix algebra, that's pretty much well, that's not irrelevant to our discussion. For those of you who are interested, this is how to do that. But as long as you get the concept of what is this transformation, what does it do to your data, and then what is eigenvalues and eigenvectors, you're good to go. Okay, now let's connect the dots, right? So I would say there are many transformation matrices out there, but there's one of them which is important and relevant to our discussion, and that transformation matrix is our covariance matrix. So let me actually write it down. Imagine you have two features, x1 and x2. What is a covariance matrix? Your covariance matrix is going to be something like this. The variance of x1, variance of x2, covariance of x1 and 2, covariance of x2 and x1, which is the same, right, as x1 and x2. So why are we interested in this transformation matrix? Because this is a matrix that is carrying information about the variance of the observations in the data, right? And we said that in the very first slide. What is PCA? What is principal component? It's a technique that helps us to reduce the dimensionality of the data in a way that it keeps most relevant information, right? So basically that means that it's trying to reduce the dimensionality along with keeping as much information as possible. And that information in this case means variance, right? So if I have a covariance matrix, if I go ahead and calculate the eigenvalues and eigenvectors, we're done. That's pretty much it, because eigenvalues of a covariance matrix are going to be those directions that are immune to that transformation. So it means that the axis is not going to change. And the magnitudes are the eigenvalues. So basically, we're going to find those magnitudes and say, hey, for example, this eigenvalue is the largest. So it means that that's going to be the most important direction in the data because it gives you the most variation of the data, right? So at the core of PCA, there is this understanding the concept of eigenvalues and eigenvectors of a covariance matrix. So here's a very simple example that should help you. So imagine we are in this two-dimension x1 and x2. Right, you can say xy, but I just want to make sure that we don't confuse it with supervised model. This is a simple x1 and x2. And imagine this is your data set, right? What's the goal? We want to find a direction or directions in the data set that explain the most variation. So our transformation matrix will be the covariance matrix, right? Because again, it carries some information about the variation, about the variance of the data. So we apply that transformation, so which is our covariance matrix. And then we look at the observations in the new space. So these are observations in the new space. For example, this one is going to go here, this one is going to go here, and etc. Right? So this is our new space. So, and that means that the principal components, these are the eigenvectors of your covariance matrix, determine the directions. So this is your PC1, PC2, and eigenvalues determines the magnitude. So in other words, the eigenvalues explain the variance of the data along the new feature axis. Okay, so now in this case we have two, let's say, principal components, PC1 and PC2. If you want to reduce the dimension of the data to 1, which of these components would you drop? Number 2, right? Because PC1 is going to be the most important one. It's reduced the data while keeping the most valuable information is still in place, right? Which is the variance along this axis. Okay. So in summary, principal components are vectors that define a new coordinate system in which the first axis goes to the direction of the highest variance in the data. The second axis is orthogonal to the first one and goes in the direction of the second highest variance in the data. The third axis is orthogonal to the first two and goes in the direction of the third highest variance in the data, and etc., etc., right? So if this is your x1 and x2, this is the original data. Here we're going to show the principal components. So this is your PC2, PC1, and here we're showing the projections along the PC1 direction. So here, the orange dots, these are the projections, right? So projections along PC1. So these are going to be the projections. And as you can see, if you look at the variance of the projections, it's maximized along this axis, right? So let me actually put it in the next slide and talk about this optimization problem. Okay, so here's the objective function. So imagine we are still in this two-dimensional space. This is our original space, x1 and x2. And we can go ahead and scale the feature. So here's going to be 0, here's going to be 0 as well. And actually, we are going to scale the features when we want to do PCA because we have to calculate some distance. And whenever you calculate Euclidean distance, for example, in two-dimensional, you will be better off scaling the features, right? So let's talk about two new terminology here: projection errors and a spread. So starting with projection errors. So what are they? Projection errors are the perpendicular distance or the Euclidean distance between the data points and the principal component. So imagine this is your principal component 1, and we want to go ahead and calculate the perpendicular distance. So this is your perpendicular distance for observation 1, observation 2, 3, 4, and etc. Okay, so these are your projection errors. So before I move forward, what do you think we should do to projection errors, right? So when you want to calculate PC1, the most important components, do you need to minimize the projection errors or maximize it? Yes, so we want to minimize these projection errors, okay? Alternatively, you could maximize something else which is called spread. So spread is the variation of the data along the principal component. So imagine, so this is your principal component and this is direction. And basically spread, you can think of it as the variance of projections as well. These are the variance. So this is your projection number 1, projection number 2, number 3 and 4 on top of each other, 5, and etc. Right? So these are the projections. And the goal is to maximize this spread. And I'm telling you that maximizing a spread or minimizing projection error, these are oops, let me actually go ahead and erase it. They're the same stuff, right? So there are two sides of the same coin, right? So in PCA, the goal is to minimize the projection errors or equivalently maximize the spread. And I think this visualization is going to help you a lot to understand it. So let's focus on minimizing the projection errors first. So in this plot, what are the projection errors? Do you agree that the projection errors are some lines? These are the red lines. So the projection errors are going to be the red lines. I want you to look at the red lines. So for example, this one, and etc. Right? Look at the red lines and then tell me in what direction, on average, the aggregate projection error is minimized. Right there, right? So here the projection error is minimized. I can say minimized projection error. Okay, and so basically this is your principal component number 1. Alternatively, let's focus on the spread. Again, look at the projections themselves. What are the projections? The red dots. The dots are the projections. And focus on the red dots and tell me at what point the variance of those red dots is maximized. The variance of the red dots, right? Look at that, it's getting bigger and bigger right there. So this is where the variance of those projections are maximized, right? So we are maximizing spread. So as you can see, either you maximize the spread or you minimize the projection errors. This is going to be your first principal component. I call it PC1. And then, for example, if you're in two-dimensional space, you have two features, you know that your second component is going to be orthogonal to the first one, so this is going to be your PC2. If you're in higher dimension, imagine you have 10 features, so you can have 10 principal components. You're going to find the first one by minimizing the projection errors, and then you're going to look at the rest of the data. Well, you look at perpendicular vectors, and among those perpendicular vectors, you pick the one which is minimizing the projection error. Then you go to the third one, you go to the fourth one, and etc., etc. Okay, we are done with terminology, and hopefully we know what is the relationship between principal components and eigenvalues and eigenvectors of a covariance matrix. So in part 2, let's talk about principal component analysis, and then basically discuss proportion variance explained, and then finally look into the scree plots. All right, as I stated in the very first slide, the goal in PCA is to reduce the dimensionality of the dataset, right? So if you have a dataset with many features, they are going to be highly correlated with each other, right? So again, if you're talking about hundreds of features, right? The goal is to represent that dataset with a smaller set of features that still does well in describing the data and explaining the variation in the data, right, in right directions. So, and we know that on the other hand, when we have many features in the data set, visualizing, fitting the model is going to be problematic, right? And basically PCA is used to summarize or transform highly correlated features of data into few main uncorrelated components. So I'm going to pause for a second here because this is important. If I have, I don't know, if we have a data set with 100 features going from x1 to x100, we know that there's a good chance that many of these things are highly correlated, right? The idea is that let's reduce this dimension to 2, 3, or even 4, I don't know, 4 or 5, so we can decide how many of them we need, right? And in a way that these things, we know that, first of all, the dimension goes from 100 to 3, and these are orthogonal to each other. So it means that these new features, these new components, we call them PC, PC1, PC2, PC3, are uncorrelated with each other. Okay, so basically how does PCA does the job? So we already talked about it. We know that we have to find the eigenvalues and eigenvectors. Then we have the eigenvalues. We can sort them from highest to lowest. And then this is going to be sorted according to their usefulness in explaining the total variance in the initial data, right? So for example, I have lambda 1, lambda 2, lambda 3. These are eigenvalues, right? And we know that this is associated with a direction that explains the most, it has the most variation in the data. This is the next one, this is the next one. And we know that these eigenvectors, for example, V1 is orthogonal to V2, and this is orthogonal to V3 as well, right? They're all orthogonal to each other. Okay, let's talk about the details. What is PC1? So PC1 is a normalized linear combination of features that has the largest variance, right? So that's why we call it PC1. So this is the direction that gives us the largest variance, right? And it's a linear, this is important, it's a linear combination of those features, right? So this is your PC1, and this is your linear combination of a bunch of x's, right? These x's can be anything, education, age, and then, I don't know, income, any kind of information you have, for example, right? And as you can see, these, for now, we're talking about the linear combination. So this is our linear PCA. Later on, we're going to say, what if you want to capture some non-linearity in the data? So that's why we have to do something kernel PCA. But for now, let's keep things simple and talk about the linear version. So as you can see, this is the extracted version of all the features in the data. If you have 100 features, this is going to be extraction of all those 100 features. If you have 200 features, extraction of all those 200 features, right? So this is the feature extraction thing, right? We're going to impose some restrictions. So for example, the squared version of those loadings should be equal to 1. It's simply because we want to make sure that your principal components are not arbitrarily large. And by the way, we're going to give them some names. So these are going to be our loadings, right? So these are the loadings of PC1. Basically tells you how much each variable, how much each feature is contributing to your PC1, right? And also note that our X features are standardized. So we're going to work with the standardized version of X as simply for computation purposes, right? And we know that the average is going to be 0, and because we're calculating the Euclidean distance, it's going to be more efficient to basically standardize thing, right? So if I want to go ahead and calculate the variance of this PC1, if X is already standardized, I know that the average is going to be 0. So it's going to give us some computation efficiency. And what is the optimization then? So the optimization is something like this. We are going to maximize the spread, maximize the variance along principal component 1, right? So just pay attention to this formula. This is nothing fancy. We're talking about the variance formula here, right? If I have a random variable z, the variance of z is going to be what? It's going to be expected value of z squared minus expected value of z to the power of 2, right? Because we're using that standardization, we can get rid of this part, and then so it's going to be expected value of something to the power of 2. So this is our expected value of something to the power of 2, and this something are simply the projections, right? So if you remember, we had something like this. So if I look into the projections, so the projection, let me actually use another color. So these are going to be my projections, and let's say this is our principal component 1. We're trying to maximize the spread, maximize the variance along that axis. So this is the optimization problem. And again, we're going to impose this thing that the summation, the squared version of the summation should be equal to 1, simply to avoid PC to explode or to be arbitrarily large. So the output of this optimization are going to be a bunch of factor loadings. We call them loadings. And if I have these loadings, it's going to give us, basically, it's going to define the direction of in the feature space that it's maximizing the variance in that direction, right? So basically give us the PC1. So, and we're going to look at a numerical example, but just remember, if you have, for example, let me use another color, let's say green. If you have 1,000 observations, and then you have, let's say, I don't know, p is equal to 20 features. When you use this formula, it's going to give you, let's say in this direction, new 1,000 numbers, right? So basically, it's gonna for every single observation, there's going to be one number attached to the principal components in that direction, right? So we're gonna call them scores, right? So actually, in the next slide, I'm gonna show you an example. Hopefully, it makes more sense. Okay, so here's the example. We're going to work with USA arrest dataset. And by the way, I'm bringing this example from the main textbook for the course, which is ISLR. So this data set contains the number of arrests per 100,000 residents for each of the 50 states in the United States. And the features are 4 of them: murder, assault rate, rape, and urban population. Okay, so this is just 3 observations, California, Florida, and New Hampshire, and obviously there are 47 more, but and these are the features. So let's call them X1, X2, X3, and X4. So the goal is to, well, we can visualize it, right? So, but we know that we cannot visualize it in 4 dimension. Now, how about we go and reduce that dimensionality from 4 to 2 and visualize it in the PC1 and PC2 space, right? So let's do that. Remember, we said PC1 is a linear combination of all those 4 features. So in this example, our PC1 is going to be equal to some loadings multiply murder. Let's call it again for the sake of simplicity, x1, x2, x3, x4. So it's going to be phi 1, 1, x1 plus phi 1, 2, x2 plus phi 1, 3, x3 and plus phi 1, 4, x4, right? So this is your principal component 1, which is a linear combination of all those features. And basically we can go ahead and calculate all these numbers in a new space, right? So, and what do I mean by that? So imagine this is our something we call it biplot. This shows both the principal component, the scores, and the loadings, right? So let's figure out what are the scores first. So remember, we have 50 of these observations, and we have 4 features. But we want to go from 50 observations 4 features to 50 observations 2 features, right? So let's calculate, I don't know, one of the states, for example, Florida. Okay, and as you can see for Florida, it seems that, I don't know, maybe principal component 1 is something close to 2.95, and principal component 2 is something close to 0, right? So Florida is something close to 0. So Florida goes from this coordinate to the new one. So let's actually look at the Florida. In the original, I'm going to call it original coordinates. It's something like this. Is 1.74, which is murder rate, 1.97, 0.99, and 1.13. We want to send it from this to a new space, which is PC space, right? And we know that we have PC1, PC2. So PC1 was 2.95 and PC2 was something close to 0, right? How do we find it? Again, this number is a linear combination of these numbers with the factor loading, right? So let's go ahead and plug those numbers, right? So I'm going to use this formula, right? So your PC1 for Florida is going to be equal to what? We have 0.53 multiplied to what? Look at the murder. It's 1.74 plus 0.58 multiply. You get the idea of 1.97 plus 0.27 multiply 0.99, and finally 0.54 multiply 1.13. If you do the math, you should get something close to 2.95. So this is how we get that. I'm going to leave it as an exercise. You go ahead and try PC2 for Florida, use these loadings, and then hopefully you get something close to 0. So this is how we transform the data from old original dimension to a new dimension, principal component dimension, and we are going to call them scores. So this is going to be called score. So this is a score for Florida in the new space. We have score from California in new space, score from Nevada in new space, score from, again, Idaho in new space, and etc., right? So we had 50 observations in 4-dimensional space. Now we have 50 observations in 2-dimensional space. So, and the plot that visualized this is going to be called biplot. Okay, biplot displays both the PC scores and the loadings. So you can look into the loadings as well. So for example, this is the loading for murder, this is the loading for assault, this is the loading for rape, and etc., right? So for example, I don't know, for murder, your loading 5 for murder is going to be equal to what? It's going to be equal to 0.53 minus 0.41. So I'm not doing anything special. This is just the first row. Okay. And this is our 0.53. So let me actually, so here is the, yeah, this is what I'm talking about, right? So the loading vector for the murder is going to be 0.53 to the right and then minus 0.41 to the down. All right. All right, another interpretation of PCA is something like this. We say that the PCA finds the hyperplane closest to the observation, right? So what is a hyperplane and what do we mean by that? So imagine this is in your two-dimensional space. Our hyperplane is going to become a line. In three-dimensional, it's going to be a surface. In four-dimensional, it's going to be something we don't know, right? But you get the idea. So this is our hyperplane which is closest to the observation. How do we find that closeness? We are going to look at the perpendicular distance, right? So, and then if you're wondering, then what's the difference between basically PCA, right, this hyperplane, and a linear regression? So I just, for some of you it's obvious, but if it is not obvious, let me actually walk you through. First of all, in linear regression, because you're wondering, okay, this looks very familiar. Isn't it like just simple linear regression? We were fitting a line going through these observations. And the answer is be careful. First, there's one obvious difference and one less obvious difference. So the first one is that this in regression, this is X, this is Y. So these are labels, these are features. Here, these are both features. And so that was obvious. What is the more subtle one? The more subtle one is that in PCA, you are calculating the perpendicular distance, right? So these are perpendicular distances. Let's say there's another one here. So this is going to be perpendicular distance. However, in linear regression, the distance is not perpendicular. These are just simply residuals, the difference between y and y hat, right? So as you can see, these are not perpendicular distances. So just pay attention. I just wanted to bring it up, in case it was confusing for some of you guys. Hopefully it makes more sense. Again, obviously there's a big difference. One of them is supervised, the other one is unsupervised. But of course, you can use PCA for a supervised data and then just apply to the features. That's not impossible. You can reduce the dimension and probably you can feed it to the model later on, right? Okay, so that was another interpretation of PCA. All right, now that we are familiar with the mechanics behind the principal components and we know the mathematics behind it, let's wrap up this section by talking about the scree plot concept. So this is pretty straightforward. Scree plots show the proportion of the total variance in the data explained by each components, by each principal components, right? So we're going to sort the principal components from the largest eigenvalue to the smallest one, and we're going to see each of those components is explaining what proportion of the variance, right? So we call it PVE, or proportion variance explained, right? So on the left, so imagine the original dimension is 4. So this means that at most we can have 4 components: PC1, PC2, PC3, and PC4. At the end of the day, again, if your feature space X has 4 dimensions, we know that if I use all the 4 principal components, it's going to explain 100% of that variation, right? But which part of it is explained by PC1? In this example, the answer is 60%. What percentage of that variation is explained by PC2? Let's say, I don't know, let's say this is something close to 20%. And let's keep it simple, let's say 20%, right? And then what percent is explained by PC3? Let's say 10%. And this one, what proportion is explained by PC4? So this is, yeah, this should add up to 1, right? So probably my numbers are not. So this is going to be 25%. And now we can make sure that the last one is 5%. Okay, so yeah, let me actually write it above them. So 60%, 25%, 10%, 5%. Okay, so this is PVE, and obviously I can report the cumulative version of that. It's easier to read that one. And so this is a cumulative version. We're going to add them up, right? So the first one is explaining 60%. The first 2 together are explaining 85% because this is a summation of 60% plus 25. The first 3 is explaining 95%. Again, 60% plus 25 plus 10, and then cumulatively it's going to explain 100%. Okay, So that's basically also very useful as well, because for example, if you have a cutoff, right, you say, how many principles do I need to explain 80% of the variation in the data? In this case, your answer is, let's say, 2 components, right? If I have 2 principal components, then I only need 2 dimensions in the new space to explain 85% of the variation of the original space, right? So if I ask you what is the optimal number of principal components here, you have to say it depends on the threshold you're looking for, right? So now obviously at some point there's not much more to add. There's no value to add more components. Look at this one, right? If you go from 1 component to 2, it's 85%. So, and from 2 to 3, we go from 85 to 95. So maybe we should stop here, right? It's not worth adding more dimension to the data because it's minimally improving the overall variation in the data, explainability of the variation in the data, right? But again, this is subjective. It depends on what you need, right? So for example, you say, imagine you have 100 features or 1,000 features, right? And obviously, if you go from 1,000 features to 3-dimension, well, you're not going to explain 90% of the variation of the data, but what if it is 70%? So I'll take it, right? So we reduce the dimension from 1,000 to 3, and that 3 components is explaining 70% of the variation in the data. So I will work with that data set, especially with that components, especially for visualization, right? Okay, that was part 2, and now let's talk about the last part. Why principal components? What are the advantages and disadvantages? Why we should go beyond PCA? So why do we need something called Kernel PCA? And finally, what are the applications of PCA? Okay, what are the advantages and disadvantages? So number 1, reducing the number of features to the most relevant predictor is very useful in general, right? It's useful for visualization, especially if you need to do 2 to 3 dimension. It's useful for basically the training your machine learning models faster. And actually sometimes even before training another supervised or unsupervised model, we can do PCA as a part of EDA, explanatory data analysis, for identifying patterns, to say something about the correlations and things like that, right? So this is and remember, if your original data set has hundreds of thousands of features, they're going to be highly correlated, and we are going to use principal components to just reduce that dimension to 2 or 3, and we know that these 3 new principal components are orthogonal to each other, right? And as I said, the machine learning models are quicker to train. It tends to reduce overfitting, especially for the models that are prone to cursive dimensionality like KNN, right? And of course, it's going to be easier to visualize if provided with lower dimension data set, right? So and pay attention, what we're talking about supervised modeling here, but you said that PCA is for unsupervised. So what's going on here? Remember, guys, imagine this is your data set, y, x1, x2, x100. So this is perfectly supervised because you have labeled. What I'm telling is that you can go ahead and, for example, use KNN, right? If you want to do k-nearest neighbors, and imagine this is a classification task, you know that you have 100 dimension, or regression task, it really doesn't matter. You have 100 dimensions, right, from x1 through x100. And we talked about it in KNN, the module, that KNN models are prone to high dimensionality. Actually, there's this something called cursive dimensionality that when it kicks in, it reduces the performance of KNN dramatically, right? So we want to say that, okay, let's look into these features, use PCA, reduce it to 3 dimensions, and then apply KNN to those 3 dimensions, right? We are not excluding any of the features, so pay attention. We are not excluding x1, x2, or something like that. We are extracting them to basically some new components. It can be PC1, a function of all the features, PC2, function of all the 100 features, and PC3, function of all the 100 features, right? And we're going to work with that extracted version and then pass it to your supervised KNN model, and we're going to look at the performance. Sometimes it improves it, sometimes it gets worse, right? Again, it depends on what percentage of the variation is explained and what machine learning models we're dealing with, right? So what are the disadvantages then? It's hard to interpret. Obviously, it is hard to interpret because remember, your PC1 is a linear function, and we said linear, right? Phi11 x1 plus phi12 x2 plus, I don't know, phi 100 x100. And there are these loadings, each one has a number, and obviously it's going to be hard to interpret this thing. And what is the unit, right? The unit is the extracted version of all the units. One is education, one is age, and so how can I read into this, right? So when it comes to interpretation, well, it's almost impossible to interpret it, right? And also note that it's the standard PCA, the one that we talked about, it's linear PCA. So this means that it is limited to linear transformation. So this means it may not capture the intrinsic nonlinear structure in the data, right? So what if the relationship in the x's were already nonlinear, right? What if there is this nonlinear structure in the data? And if you apply a linear combination of a bunch of x's, still it's going to capture the linear relationship. So the trick is that we have to go beyond standard PCA. We have to go beyond linear PCA, and we will talk about something called Kernel PCA, which is going to solve that. So basically, it's going to look at the nonlinear relationship between x's and work with the extracted version of those things instead of the linear version of them. Okay. Okay, so in order to understand the kernel PCA, we have to first talk about kernel trick. So what do we mean by kernel trick, right? So actually, let me show you a very simple example. Imagine we have some observations like this, and as you can see, the red dots and the blue dots, right? And this data set is non-linearly separable. It means that if I go ahead and use a linear classifier, no, I don't know, anything I use, it's not going to be able to separate the blue dots from the red ones, right? So we need a non-linear decision boundary to do the job for us, right? So basically we know that this is the answer, right? But how do we get that, right? So the answer is we have to go to higher dimension. So imagine, I don't know, this is x, this is y. It can be x1, x2, it really doesn't matter. So here, imagine this is xy. If I go from this 2-dimension to 3-dimension, basically I come up with a formula, z is equal to x squared plus y squared, right? And then calculate the new values for z, we will get to something like this, right? We get to something like this, right? So this is your z is equal to x squared plus y squared. Basically, for any point, we can, so this is our, I don't know, this is your x, this is your y. You can go ahead and calculate z. Z is equal to x squared plus y squared. This is your x, this is your y. You can go ahead and calculate the value of z for that observation, right? If you do that, it will become something like this, right? So basically, again, x, y, and z now. Now, if you pay attention in this new space, in this new higher dimensional space, it is perfectly separable. The data is perfectly separable. I can go ahead and use this green hyperplane and then separate the data. So that was a simple trick, right? And but the problem is that the seemingly simple calculation, if you want to go from 2-dimension to 3-dimension, maybe it's simple, but what if you have to go from 3-dimension to 10-dimension to 15-dimension to make sure that the data set is linearly separable. So that's going to be computationally expensive, right? Again, this new feature space with higher dimension, in that new higher dimension, the data set is linearly separable, but this operation is expensive, it's computationally expensive. So what should we do? The solution is something called kernel trick. So kernel trick is going to do the job. Basically, it's going to go ahead and find this decision boundary without going to higher dimension space. So this is at the core of kernel trick. So again, I repeat myself, it's going to come up with a nonlinear decision boundary that helps you to basically, imagine this is a classification task, right? It helps you to separate the data without going to higher dimensions, right? So it's going to give you this boundary, without without the need of going to higher dimension. So let's see how it's done. So when we're using the kernel trick, there is this thing called kernel function, that the role of the kernel function is to go ahead and assign a number to every single observation in the data after applying a function to that, right? So there are going to be different types of these kernel functions. So I'm going to show you the details of the RBF, radial basis function. And there are a couple of other more. There's sigmoid kernel function, there is polynomial, and etc., etc. But the goal is very simple, actually. It's very intuitive. So here again, imagine this is our data set. It's obviously non-linearly separable in two-dimensional space. And remember, I promised you, without going to higher dimensional space, we are going to figure out this decision boundary, right? So for example, so how it's done. So RBF is basically something like this. It's going to go ahead and assign a number to every single of these observations, right? So let's pick one of them, for example. I don't know. Let's say, so first of all, here's the formula for the kernel function is a function of x itself. And remember, this x is just the location of your observation. So for example, this is our x1, 1, x2, 1, right? And these the x's are features, right? And basically, so that's x, and then there's something called landmark. Don't worry about the details of this part. Just try to understand it at a very high level. So in this case, our landmark is this red circle here. Again, there is another optimization problem for finding the right place for the landmark itself, but for now, let's take it as given, right? So it's going to go ahead and take that x, that coordinate, and the landmark coordinate, and calculate this formula for that, right? So, and basically what does it do? It's going to assign a number to this observation, right? So it's going to say, hey, look at and as you can see, it's a function of the distance between x and L, right? Again, this is an example for RBF, right? So in a nutshell, if your x and the landmark are far from each other, this numerator is going to be a large number. E to the power of minus large number is going to be a smaller number. Okay, so if your kernel function is small, this means that we are further away from the landmark. However, if, for example, let me use another color. If you're here, pay attention to, let me use my laser to see what I'm talking about. So the purple one, right? If you're here at that purple point, and if I go ahead and calculate this one, so let's say x and the landmark are pretty close to each other. So the numerator is almost close to 0. I get e to the power of minus, I don't know, something close to 0. And whatever we have here, it really doesn't matter. So it's going to be e to the power of 0. It's going to be 1, right? So when kernel is equal to 1, basically you are very, very close or right at the landmark. You're here. Okay? So as you can see, it's assigning one number to every single observation. If that number is large, we are here. If that number is small, we are here. Okay, so and then with that you can figure out what is this, right? So again, you can come up with a threshold. If it is less than a number, call it one class. If it is greater than a number, call it another class. And this is how we're able to separate this non-linearly separable data set in two-dimensional space. And remember, we didn't go to higher dimensional space, right? We just we stayed in that two-dimensional space in this example. We used a formula called kernel function to assign some numbers to that. So that was pretty much it. Okay, so there are different types of kernels as well. So this is our linear kernel. Linear kernel is not going to do anything. It's just using a linear combination of all those observations. So our linear PCA, our standard PCA was using this, right? And the rest of them, this is what we call, if you use the kernel trick, any of these ones, and apply to PCA, it's going to be called kernel PCA. So this is the RBF. We look into the details. This is polynomial kernel, sigmoid kernel, and of course there's a formula for each of these things, right? So for example, for the polynomial kernel, and if you're interested, if you're curious to know, there's a formula for the kernel. So x and y, imagine there are 2 points. It's going to be a summation of xi, yi plus c to the power of 2, right? And for For the example that we had, instead of RBF kernel, I could have used the polynomial kernels. Remember, we said go to this higher dimension, x squared plus y squared, and then find the basically hyperplane that separate the data and then project it back. So now we're doing it without going to higher dimension, right? So we're simply calculating assigning some new numbers to every pair of observations. All right. So what is Kernel PCA? Kernel PCA is an advanced form of PCA that utilizes kernel trick or kernel method to enable effective dimensionality reduction in a dataset with complex and nonlinear structure. So basically, in a nutshell, if you know that, or if you think that there's this nonlinearity structure in the dataset, applying linear PCA may not be as effective as you think, right? So for example, you go from 20 dimensions to 3 dimensions to 4 dimensions, and it really doesn't matter. So for example, the first 2 or 3 principal components is just capturing 20% of the variations in the data. If that's the case, it's a sign that there's nonlinearity in the data set, that your linear PCA is not capturing it, right? So what is the process? Actually, it involves 2 steps. One is kernel transformation and the other one is dimensionality reduction. So this is slightly different than simple PCA. In simple PCA, we just calculate the eigenvalues, eigenvectors, and then we're done, right? So here we have to do one extra step, which is finding the kernel transformation. So what is this? So the idea is to apply that function. Remember, we talked about the RBF, but it can be RBF, it can be polynomial, sigmoid, you name it. We apply that function to the original data. And this is going to create a kernel matrix. By the way, we call it gram as well, so gram, that represents similarities between all data points. So this is pretty straightforward, don't overthink it. So imagine, I don't know, we are in 2-dimensional space. We have x1, x2, right? And so, I don't know, this is the data. I'm just making up some stuff. And we can go ahead and apply this kernel function, whatever it is, okay, to every single pair of data. Let's say I have 100 observations, right? If I apply this kernel to those 100 observations, so it's going to give me a matrix. And this matrix is, if I have 100 observations, it's going to be 100 by 100. So literally is looking into every single pair of observations and tell me if they're similar or not, right? So imagine along this diagonal, right? So observation number 1 to itself, obviously the kernel function, if it is RBF, it's going to return 1, right? It's pretty similar. Each observation is similar to itself, right? So all these numbers are going to be 1. And off diagonal are going to be some numbers less than 1. Okay, of course it's symmetric. Okay, so basically, this is one pair. I don't know, maybe this is this pair. Here's another pair. Let's use another color. 2 observations, maybe that's this one. I don't know, 0.2 here, right? So it's going to give you 100 by 100 matrix, which is, again, this is the dimension of this is the size of your data set, right? Don't confuse these things. So the dimension is equal to 2 here, size is equal to 100. This matrix is 100 by 100, right? And then in the second step, we have to apply our dimensionality reduction, our PCA, to this kernel matrix, right? So if I have a 100 by 100 thing, kernel matrix, how many PCAs can I have at most? That depends on the rank, right? If the rank of this matrix is 100, then I can come up with at most max 100 PCAs, right? Or PCs, principal components, right? It can be 1, it can be 2. Well, we can go all the way to the 100 if the rank is 100, right? So that's the difference. And so what is important here is that, let's say this is 100 by 100 and I work with PC1 and PC2. This PC1 and PC2 is being derived from this transformation matrix, and this transformation matrix has all the information we need to summarize the nonlinearity that's existed in the data set, right? So basically these components that we create, let's say PC1, PC2, are going to capture all those nonlinearities, whatever they are, right? Because we apply the Kernel PCA to create that kernel matrix first. Okay, now this is everything you needed to know about the PCA and Kernel PCA. Let's look into some applications and wrap up this section. So the first example that I'm going to show you here is from the CFA reading textbook, and it's basically looking into a data set for two portfolios. One is a portfolio of 500 large cap companies we show with DLC, and the other one is a portfolio of very large cap companies and 30 of them, right? So the data set exists of index prices and more than 2,000 fundamental and technical features, moving averages, indicators, macroeconomic variables, and et cetera, et cetera. But the point is that it's 2,000. So the dimension of the data set is 2,000. This is very, very, very highly dimensioned, right? And especially if you want to think of interpretable machine learning, it's really hard to do anything with this data set, right? And we know that if the data set is highly dimensional, the multicollinearity among the features is almost inevitable, right? How do we fix it? We can apply, for example, PCA to reduce the dimension to, I don't know, 5, 4. Remember, we are going from 2,000. And basically, hopefully, we can keep the variance in the first 2 or 3 dimensions as well, right? Let's see if that's the case. So if we plot the scree plot, we're going to see that this is actually very exciting for these two portfolios, right? And I'm going to go ahead and show, imagine we went from 2000 dimension to 20, right? We calculated the principal components 1 through principal component 20. All right, and then we are looking into the scree plot. What percentage of the variance is explained by the first component, second component, etc., right? And as you can see, the first 3 components together, or maybe the first one is 45%, the second one is 30-something percent, the third one is 20%. The first 3 components is explaining almost 90% of the variance. Just bear with me. We go from 2,000 dimension to only 3 now, and you're explaining 90% of the variation in the dataset. This is excellent news, right? So this is for the DLC 500, the large cap companies 500. And then if we apply it to the very large cap companies, it's still there, right? The first 3 components combined collectively is explaining 86% of the variation in the data. So this is great. This means that if you need to do any kind of visualization for the data, or if you go to 3D dimension, 3D visualization, you are basically talking about explaining 90% of the variation of the data. So whatever it is, whatever you expect to see in terms of the number of clusters in the data, and et cetera, it's going to be there. So this was one example. Here's another example where we're going to combine PCA with a supervised learning model, right? So let's see how it's done. So imagine, let me actually show you the entire thing. So imagine your original feature space has dimension of 100. Okay, so we have x1 through x100. Obviously, we cannot visualize it. We cannot do any kind of clustering. So let's say go ahead, use PCA. We're going to apply PCA and come up with 2 components, PC1, PC2. Now in 2 dimension, we can plot it, right? So imagine this is our principal component 1, principal component 2, and then we now after that, so far it was unsupervised. And after that, we can go ahead and apply something like k-means clustering to that. So k-means, we haven't talked about it yet, but this is something, a clustering technique, right? So basically, we're going to come up with 3 clouds of data, right? 3 cluster of data, right? And if there's labels, which there is labels in this case, because how do I know? Because these colors are different. So we have green, orange, blue. So this means that these are labels. So that means that we can now have classification, right? So maybe this is class 1, class 2, class 3. Okay. So again, this was another application of PCA. Okay, and finally, let's look into an example of Kernel PCA, right? So here's the idea. What if we want to use a linear classifier, but the data is non-linearly separable? So what can we do? So here's an example that I'm going to replicate it in Python next class, but basically what we have here is, just, let's say for the sake of argument, we have only two features, estimated salary and age, right? And I've already went ahead and scaled these things, so that's why we have 0, 1, plus 1, minus 1, and etc., right? So both age and estimated salary are scaled. And imagine this is the data. I want you to just focus on the dots, right? The green dots and the red dots. These are the observations, actual observations, right? And if I want to come up with a classifier and the data set is obviously nonlinear, what can I do? So I cannot use a linear classifier, because if I use a linear classifier, I will end up with getting something like this. This is my logistic regression, okay? What are the solutions? I can do two things. Do not touch the data, but go from linear classifier to nonlinear classifier, right? So what are those things? For example, I can do decision trees. So it can do something like this, and probably it's going to do a good job. I can do polynomial logistic regression, something like this, right? And so that's if you want to stay in the same dimensional space, right? If you want to stay in the same axis, age and estimated salary, you can change your model to use a nonlinear version, again, like decision trees, right? So that's one way. Another way is that use the same model, don't touch the model, use the same linear logistic regression, but go to PCA axis, right? Principal component axis. What do I mean by that? I'm going to use a kernel trick to transform all these observations. Let me actually show you what I mean. Yeah, we're going to take all these observations and apply kernel PCA to them, and then plot these scores in a new dimension, PC1 and PC2, right? So this is your PC1 and PC2 dimension. And as you can see, again, guys, these are the same observations. If I have, I don't know, 2,000 or 1,000 observations here, obviously I'm going to have 1,000 observation here, but pay attention to the axes are different, right? If I apply the kernel PCA, the kernel PCA is going to capture this nonlinearity in the data set. And when I project it back into, I don't know, 2-dimension, it's going to be something like this. This new data is more linearly separable, if you wish, right? So if you don't want to change your model, so you like logistic regression because it's simple, it's efficient, and it's interpretable, you can still use that, but you have to apply kernel PCA to capture that nonlinearity in the data. And now hopefully a linear model is going to perform better. So this is another application of kernel PCA that I'm going to go ahead and replicate it in Python next time. All right, that concludes our module number 11, dimensionality reduction using principal component analysis. In the next one, which happens to be our last module of the course, we will be talking about clustering techniques. Specifically, I will cover k-means and hierarchical clustering. Until the next one, take care.